I welcome all of you on platform of Your PD Education, and you are watching the regular videos based upon the various actual questions asked in the interviews. As you know, Your PD is the platform which prepares you for various interviews, guides you for preparation of various interviews, and this particular question is for Bhava Atomic Research Center. So these questions are on the basis of the feedback we get from our own students who go to these interviews, and every interview has a little different approach from others. Like BARC is a very in-depth kind of interview. Maybe in 1 hour they will ask you only 4 questions or 3 questions, but they will keep on digging you down. They keep on asking you questions from further from your answers. So that is how they take you in deep analysis of particular topic. So this particular questions in BARC was from stress strain diagram. So as you can see, stress strain diagram, the typical stress strain diagram which I am showing here is of mild steel, and mild steel is the this is the engineering stress strain diagram, which is also called a nominal stress strain diagram, in which you take the original area and original length of the gauge, that is gauge length, gauge diameter, and then you plot this graph, and then it has two main parts, elastic limit and plastic limit. Plastic range is also divided into two parts. One is strain hardening, then is necking. So what we understand is, like in the strain hardening or work hardening region, which is from yield point to ultimate point, the strength of the material tends to increase from yield strength to ultimate strength. So this is that region which is called strain hardening region. Now in this region, as we know, yield strength, which is the design strength of the material, that tends to increase to the ultimate strength. Now this is a typical metal forming operation, like hammering or rolling, forging, in which grain entanglement, grains get entangled into one another, and that is one of the main reason for increase of this strength. Now what we know is, like in mild steel, there is a region called strain hardening region in the plastic zone, and then in that region there is an increase in the strength of the material. Now we also know that stress strain diagram, slope of stress strain diagram is nothing but that is a Young's modulus, that is a stress per unit strain. So somewhere Young's modulus is some kind of parameter to tell us about the strength of the material, or to tell about the rigidity or stiffness, or these parameters. As you know, E into A is axial rigidity, EA by L is the stiffness, those things. So that means a material having high value of E is also a stronger material. Now listen carefully. The slope of this stress strain diagram in the elastic region remains same, and through Hooke's law we calculate that as modulus of elasticity. Now the question is, in the strain hardening region, which is like this, the slope of this stress strain diagram is continuously decreasing, and at the top point, ultimate point, it becomes 0. Now the question was, in the strain hardening region, what happens to the strength? Sir, it increases. What happens to the slope of the graph? Sir, it decreases. What normally slope gives you? Sir, Young's modulus. Though Young's modulus is given only in the elastic region, in the plastic region we cannot call it Young's modulus, but there is some kind of similarity. So when the slope of stress strain diagram in the region, strain hardening region, is decreasing, what is the meaning of that? Slope becoming 0 means this material is not now stiff or something like that. So how do you justify strength is increasing but stiffness is decreasing, or elasticity, Young's modulus is decreasing? How do you justify that? There are two answers to that. Number one, no doubt immediately after strain hardening region, stiffness, this necking region starts. So that means the stiffness of the material actually is decreasing. If the material is stiff, it will not neck, it will not go for necking. Stiffness is decreasing, no doubt about that. Number two, this is not the actual stress strain diagram. This is not a true stress strain diagram. If you plot the true stress strain diagram, this will be in the strain hardening region something like this, and that means its slope will not be decreasing. So the true stress strain diagram gives you an idea that yes, the stiffness is not decreasing in this region. So the BRC question was about the strain hardening region, slope of strain hardening region, and what is the meaning of slope of strain hardening region decreasing and becoming 0 at the top position, ultimate position. This was a really good question, and the moment you start giving answer, they will dig you further, they will keep on asking you further what is the meaning of negative slope in the necking region or something like that. So stress strain diagram, as we study in our engineering for other exams, in BARC you can expect that he will go into deep of that. And research organization like BARC, ISRO, DRDO, they will enter into physics part, and the moment they enter into physics part of engineering, that simply means microscopic analysis, not a macroscopic analysis only. Microscopic analysis means molecular level pe they can enter and they can ask you questions at the molecular level also. So you need to prepare on those lines. Hope you understood this question. Just read in detail about this, because BARC is a different kind of interview. Thank you.